So a few words on GRAM. It's a musical institution. It's a little bit like IRCAM. We have both artistical and scientific and research activities, but it's, let's say, 10 times smaller. But it's supported by the Ministry of Culture in France, the Auvergne-Rhône-Alpes region, and the city of Lyon. And on projects, for example, like Faust, we have support of the National Research Agency, that's from research project in France. So as Jean told you, I will try to, first of all, I have 1 hour, but it's 1 hour just after having lunch, so it's dangerous hour, so I hope that, well, I will look at you and try your body to feel asleep during the presentation, and I will try both to be a hand-on session, so that you can try using only online tools, and also I will at the end make a kind of demo of additional tools so that you don't have to install anything, but have a recent browser that supports typically ASNGS and maybe WebAssembly. But ASNGS would be enough. So who is doing audio programming in some language? Okay. Now I'm going to ask who is doing Faust audio programming? Okay, so we have plenty of people to convince about the interest of doing Faust audio programming. So what is Faust? Basically, it's a language to describe electronic music instruments and audio effects, etc. Obviously, as you well know, it's not the first programming language to do music or audio. There are plenty of them, and the most popular are Max, Pure Data, for the audio domain or the real-time domain, Pure Data, Super Collider, C-Sound, Chuck, and Faust. But Faust was the first one to be fully compiled. So it means that Faust can be used when you need a sample level semantics. All others are based on vectors, so you cannot do filters, this kind of stuff, because they need to amortize the cost of the interpretation, so to speak, of the language. Faust is the first one to be fully compiled. Now there are other languages that are compiled, like Gen in Max MSP, Chronos, and some other languages. And Faust is also less general, so usually you don't do a whole piece using Faust. Many people, for example at GRAM, many productions are based using Max and Faust. So you use Faust to do some part of the piece, the signal processing parts, not the whole piece. So the idea of Faust is to offer an alternative, a high-level alternative to C++ or C development. The people who are targeting are typically what in French we call the RIM, réalisateurs en informatique musicale, which are computer music producers. So people working with artists and with composers that do all the technology of the piece. So they have a very good knowledge of signal processing, but they are not computer scientists. They know how to do max patches, but not doing C++ or C, etc. So the idea is to target this kind of people. Another point in Faust is it's a specification language. So you have no control on how the code is generated, so to speak. And the idea is that the technology is doing the right thing and generate efficient code. It means also that two different Faust programs with the same semantics should result in the same generated code, in the same compiled code. So it is used on stage for many artistic productions, but also more and more in education, because you are quite close to the math, so you can explain signal processing algorithm and then switch to an implementation quite easily and have something that runs in real time. Okay, so typically it's used for artistical production like sound installations, or this one is interesting because it's a concert we did in 2014, and it was a concert with smartphones, and the audience was participating with the smartphones. But if you develop applications for smartphones, you know that it's quite challenging to develop an application for a smartphone. And with Faust, we have all the technology to do that quite easily. And so people that are not, again, computer scientists can create native applications for smartphones to audio instruments on smartphones. It's used in several open source projects. For example, here it's the Guitarix project. It's a well-known project on Linux, and most of the effects that are embedded into Guitarix are made with Faust. And these allow people of other community, for example, Super Collider or Pure Data, to take all the code of the Faust code of Guitarix and recompile them for their own environment. More and more, we are interested in targeting web applications. So there is a conjunction of several technologies that are more and more efficient. For example, some years ago appeared the Web Audio API, and at the same time you have also ASM.js. Who is familiar with ASM.js? Okay. So by combining the two, you can create JavaScript nodes. So in the Web Audio API, you have native nodes, but you can create your own nodes, but using JavaScript. But obviously, if you use plain JavaScript, it's already slow. But with ASM.js, you can achieve good performances. So we have a backend for generating ASM.js code. And very recently appeared WebAssembly. Who is familiar with WebAssembly? Okay. Which is even, it's going to be much better supported than ASM.js, and it's already faster than ASM.js. So we can generate real-time audio application for the web using the WebAssembly backend, and have performances which are maybe only 2 or 3 times slower than native application, which is very good for. So this is really very interesting. For example, this application here, it's a web page. It's the guy who developed this simulation of the YC20 Yamaha synthesizer. He had his own version of the real synthesizer, but the real synthesizer was dying, so to speak. So he decided to make a virtual copy of the synthesizer, and it used Faust for that. So he made a VST plugin that is compiled to C++. But then when this technology became available, he recompiled it for ASM.js. And now there is a web version of the synthesizer. So if you go to the web page, so you can you have realism, for example, that mimic the noise of the synthesizer that you can more or less remove. You can plug a MIDI keyboard and you can just start playing with this synthesizer. So the technology is not, it's far from being perfect right now. There are several technical problems remaining, but it's going to be more and more interesting. So it's very interesting. It will change the way we use software, because we will use musical software just by opening a web page, and without, on all platforms, and without anything to install. So this is going to be very, very interesting. Okay, so there are many interesting projects in sound spatialization, in particular in ambisonic projects. This project here, it's also quite fun. It's a brain stethoscope. So the idea is to sonify the brain activity, so to speak, and discover some irregularity with the brain activity. And all the audio part is done using Faust. Karma, they are doing a car simulator. And all the audio engine of this car simulator was developed in Faust, for example. This is another interesting project where you start with the CAD file of an object and you transform it into a Faust program that do the sound of the object, for example. We have more and more projects where a very specialized approach that generate code for Faust code. So higher level compilers, so to speak, that target Faust, because then Faust can target a large variety of targets. An interesting application is also this Sonic Cloud application, which is a kind of Skype system for people with hearing problems. And all the audio platforms of Sonic Cloud is also developed using Faust. There are also some commercial applications that are quite nice. In particular, this one. Have you ever seen this GeoShred application for iPad? No? Okay, so it's let me play a little bit of. So all the audio engine is, there is no sampled sounds, everything is done in real time using sound synthesis models, and all the audio part is written in Faust.
I know to play guitar.
No, he's keyboard player.
He's keyboard player.
But it's not that obvious.
I'm sure it is.
It's
How many years he practiced?
no, not yours, because the application is quite recent. Another one also by Beaufort is this one, which is a guitar simulator. Which is also very fun to play, easier to play.
This is Beaufort's virtual guitar, power chord for mobile and tablet devices. What makes power chord unique is that unlike other virtual guitars that simply play back recorded samples, power chord models the physics of a real guitar. Power chord provides an unprecedented interactive playing experience using feedback, distortion, and effects. It can be strummed in different positions. The strings can be scraped. And you can even play harmonics. One of the most fun things about playing power chord is interactive feedback and distortion modeling.
audio part is written in Faust, but there is an incredible amount of fine-tuning and to find something that sounds so well. Most of the audio part of this application are developed by Julius Smith, which is a professor at Stanford and at Karma, and also one of the main contributors of the Faust library. So in principle, in the Faust library we have everything to do that, but I must admit that I never figure out how to do that exactly with the same quality. So again, a lot of work to fine-tuning all the parameters to make things sounding so well. Okay, so now it's time for you to make an exercise. So we're going to go to the online compiler. So the online compiler is here. faust.com.fr/online compiler. By the way, since we are all on the same computer, which is a small machine at Grano, it can crash, and if it crashes now, then I'm fucked, and you also, because it's going to be complicated to continue the demo. So don't do very weird stuff, and don't try to crash please. Okay, so I would like you to enter a program and to make it run, okay? So the program to enter, it's just one line, well, 2 lines, well, 3 lines, okay? So import, then after I will explain all the details of the language, but just to have you the feeling of doing your own program and having it to run. So you can just type, so don't forget the semicolon at the end of every Faust statement.
C-like.
Huh?
It's C-like.
Yeah, I like redundant syntax, so to speak. So the first statement, import the standard library with where everything is defined.
Spacing significant?
No.
So it is one line.
Huh?
Yeah.
Yes, it's one line from this point of view. So in principle, if I copy, or I can just type the code myself. So once you have the code, let me type the code. So import std Faust not even. And then we have to define process. So process is the equivalent of main in C, okay, the entry point. So a Faust program is basically a list of definition, and at least you need to have the definition of process, the main entry point. So here we have button, play. Then command, it's like the Unix pipe. Okay, we will connect the output of button to the input of the right expression, which is pm.djembe. So the first parameter is the pitch, then the other one is the position, the other one is how sharp is the strike, and then the gain. So in principle, this should compile. So let's try to compile the code. Okay. So here you see the C++ generated code for this example. The code generated by Faust is independent of any library. So it has a fixed memory footprint. There is no dynamic allocation at all, fixed CPU footprint, and is completely independent of any, apart the math libraries. Okay. And so the code basically, the interesting part is the compute method. So it's where the computation happens. So you call compute to get the next maybe 256 samples that you want to compute. So you have a single object, a class that you can initialize to initialize the internal state, and then you call compute repeatedly to get the samples. Okay, so you can generate code for various languages. So if you are not familiar to WebAssembly, if you choose WebAssembly, you will see that it looks like Lisp a little bit. So this is the textual representation of WebAssembly. There is also binary representation of WebAssembly, which is obviously faster to load by browsers. Okay, so you can have a look at the graphical representation of the Faust program. So Faust is a textual language, but it has a straightforward graphical translation. So you see here, we have the button and the djembe. Everybody is able to have the code, to compile the code, yes? You can navigate into the block diagram by clicking on the blue, okay, so you see that your trigger, a strike, and the djembe model here. You can click on the djembe model, and you see that it's a bunch of resonant filters in parallel. This is called modal synthesis. So it's not very good djembe, but okay. You can have a look also at the task graph, which is interesting because it shows you what can be computed in parallel. So you see that all this part here can be computed in parallel. And we have automatic parallelization in the Faust compiler. So for example, if you use the option -OMP, you generate OpenMP code, and that runs in parallel. Yes, oh yes, this one is, and then you can ask for the signal graph, which is huge. I think that everybody is doing the signal graph at the same time, so. Which is really basically the circuits, how it is implemented. So let's say that you would like to make a VHDL version of the program, and you will use this description, so to speak. So it's really the circuit. Okay, so but what we want to do is to execute the code. So we go here to exec, then we choose web, and then you choose audio, and that's it. It has generated a WebAssembly version of the program, and this code is embedded into a web page with a kind of not very nice user interface, but it's automatic user interface. So here it's the program.
Did we all get the same program
Yes.
to cache the...
No, this one will not cache anything, but there is another, the Faust server, which is a different, will cache the code. Here it will be recompiled.
Your QR code looked the same as mine.
My QR code, where do you see a QR code? Okay, here. In principle, it should be different. Is it really the same?
Maybe not. There was a few parts of it. So.
Okay. Yeah, that's probable. Okay, so everybody is able to have this program running. So excellent. You did your first Faust program. So I will come back in half an hour. Okay. So here is the program. Okay. Just for you to have the feeling of what it looks like to create a Faust program. And now I'm going to explain in more details how the language works. Okay. So the first thing is that so Faust is a Faust program describes a signal processor. So I'm going to explain what a signal is, what a signal processor is. Then I will explain that on top of that we have the algebra of to combine signal processor together, and then on top of that we have user-defined functions. So in Faust, so a signal is a time to sample function. In this version of Faust we are mono-rate, so all the signals have a single rate, but we're working on a multi-rate version of Faust. And currently we have two types of signals, integer signals and floating point signals. The point is that it's a function on also on negative time, but negative times, all signals, the value of any signals at negative time is always 0. So this is why if, for example, here you see process equal 1, it's a Faust program. The 1 in Faust is not the number 1, it's the signal processor 1. A signal processor that takes an empty couple of input signals and produce one output signal. And this one output signal is a function that will be 1 from time 0 to infinity. Is it clear? So programming in Faust is essentially combining signal processor together using primitive signal processor. So what do we have? We have all the arithmetic operations, but instead of being on numbers, they are on signals. So all the math operation. When you compare to signal, the result is a signal that kind of Boolean signal that is 1 when the condition is true and 0 when the condition is false. Okay, all the other operations.
These are integer time, not continuous time signals.
Yes, integer time, but on the multi-rate version, it's not going to be integer time anymore.
Actually, this is routinely done. It would probably be very easy to make a proper Haskell front-end of Faust, so that people who are addicted to Haskell syntax can just type on their own calculators.
Yes,
and
probably.
generate Faust.
Now we were discussing of this. It's probably not very difficult. We have an embeddable version of the Faust compiler, so this could be embedded into Haskell as a library, and then you could enter Faust code either by combining things in Haskell and then try to compile that to audio code. Okay, so these are specific operations. I will come back to that. But the important operation here is the at operation. It's the delay line. So the delay line takes two signals. One is the signal that you want to delay. The other one is the amount of the delay that can change in time. And then you have the delayed signal. And the point is that because this amount of delay can change in time, the compiler needs to compute the boundary of any Faust expression so that it knows the minimum and the maximum value of a signal in order to allocate enough memory to store the delayed signal. And then you have user interface elements. So basically in Faust you describe a very abstract user interface. You say, okay, here I want a slider, here I want a button, etc. But the interpretation of how to build the user interface is not part of the generated code. It comes from outside. I will show you how this is done. And this is very interesting because somehow you separate the computation itself from the user interface that control that computation. And you can have several user interfaces, graphical ones, network one, HTTP one, OSC user interface, etc. Okay, so we are going to see how to use this user interface element by extending a little bit the djembe model. So the first thing we are going to do, you see here, instead of just having the play button that we press, we're going to multiply. So a button, when you press it, the output signal goes to 1. And when you release it, it goes back to 0. Okay? So when the button is not pressed, it's always 0. Okay? As soon as you press, the signal goes to 1, stay on 1 while the button is pressed, and then go back to 0. So we are multiplying this by this expression here that creates a pulse signal. So the period of this pulse is this number here, 4,800 samples. And the portion of this period where the signal is 1 is 100 here. Okay? So by doing that, while I press the button, I will repeat the generation of the djembe, the triggering of the djembe. So instead of just triggering every time I press, I trigger it repetitively while I get the djembe pressed. Excellent. Okay, so let's do that. Okay, let me, so here, my glasses.
I have an error in sequential composition.
Ah, you have an error in sequential composition. Okay, so that's very good.
I'm sorry, it doesn't feel very good.
You do need this kind of
You
flash.
need, in France, we have a very old this anime cartoon called Les Shadocks. So Les Shadocks, it was something very crazy. France was divided in two parts: those that loved the Shadok and those that hated this cartoon. But basically, they were in a very strange planet, and they have to escape to that planet. But they were able to build a rocket to escape that planet. But they know that the rocket was failing. The probability to have it to run was 1/1000. So they decided to do the 99.9 failure as soon as possible to go directly to the one that does it. So it's good to have failures. Okay, so check that you have here a comma, and that and here the expression is P. What is the expression again? PM. No, BA. Okay, please. BA dot pulse n, then 100.
Not pills, that's something.
And then, well, this value is quite arbitrary. And that's it. And then you need to multiply. Maybe this is what you forget. Then you connect this into a multiplication. Okay?
The type error. I had a type error.
Yes, exactly. Okay, so if we look at, we can try to compile the code, see if it's compiled. Okay, let's go back to C++. So let me show you if you compile for OpenMP. So here you can add the -OMP, and you can recompile the code. And now you have parallel code. The code is big, but here it is. So you have the OpenMP pragma. Who is doing OpenMP? No problem. Okay. Okay, so if we go back here,
You need brand new browser, it seems.
I need a brand new.
Safari is dying with OMP
Uh,
option online.
okay, so now, yes.
So it sounded like the quality of the tone bar of that was changing over time.
Yes, exactly. Because there is randomness into the way the tone is generated. So it's not always exactly the same.
Can I ask a funny question?
Yeah, funny?
It should be, hopefully. Does it matter which order you do the multiplication?
No.
Doesn't matter. Not drop down.
Well, the mathematical properties are preserved more or less. Well, more than this.
So I see that you do you create the two signals and then you combine, then you connect them to a multiplication operator.
Yes, exactly.
Can you not? Is there a way to write that in fix or not?
Yes. Okay, good question. Let me show
Because when I was
you.
writing that, I would find it easier to read if the multiplication was written in fix.
Yes, in some case it's better to have infix notation, and in some cases it's quite convenient to see the different steps, like you pipeline transformation, so to speak. So the infix notation is quite simple in this case. You just replace this by multiplication sign. That's this example. And you remove this part here. And
That produces the same block diagram. does it?
exactly, the same block diagram, the same code. So the one of the source of inspiration of Faust is FP. Someone is familiar with John Bacchus FP? But it's also a very traditional way for musicians to see when you are in the studio and you are connecting the old time of analog equipment, you were connecting them, you are patching and you are composing functions. So it's very convenient to think in terms of function composition. Okay, so let's go back to this. Now we are going to.
One question.
Yeah.
I tried to make a very fast pulse, so reducing this 100.
No, the 100 is the period where the period is the second number.
Okay.
And this is the period where it's at 1. Okay, so now the idea is that to see how to use the sliders. Okay, so instead of having a constant here, you're going to edit the code and replace this with a slider. So sliders. So here what you should do. So you see here this value is replaced by a slider. So you have horizontal sliders, H slider. The first parameter is the name of the slider. The second one is a default value of the slider, the value that the slider will have when you start the program. Then the minimal value, the maximal value, and the step value. Okay? So basically you can choose to replace one or all of these parameters with sliders and see what happens.
That's cool.
It was better with symphony, in fact.
Is there a difference between H slider and checkbox, or could you put either in either place?
Sorry?
Like is H slider a different kind of thing to checkbox? Because checkbox created a signal, whereas H slider seems to be used as a parameter. Or can you just use either?
No, you can use either. It just the checkbox is something that deliver a 1 when it is checked and a 0 when it's not checked. That's the only difference. And the slider deliver all the values between the minimum and the maximum.
So there are no numbers, there are only signals, right?
Everything in Faust, everything is signal. The main difference, if you are familiar with super collider or C sound or this kind of language, there is a difference between control rate language signals and audio signals. In Faust, conceptually, there is not this difference. It's only a difference in the compiler, so to speak. So the compiler is able to infer that the sub-expression only use constant values and slow sliders, and then he does the computation once per block instead of once per sample. But from the user perspective, there is no difference. Yes.
Is it possible to name the value of the signal so you can use it in two different places?
Sure. You can.
You can really just make
Yeah,
another definition.
You can create a new definition. So, for example, here you can insert frac equal and you give the slider. So, the way Faust is also very inspired by lambda calculus and the idea of anonymous things in lambda calculus. The fact of naming is just a inconvenience, so to speak. It doesn't declare anything. So you can name something and it's the same thing as using the definition or the name. It's always the same thing. Well, unless you have local definitions, obviously, but well, the same thing.
Does that mean there's like a... So suppose instead of that I had some signal and I wanted to vary the frequency according to that signal. But I didn't want to give that signal a name, I just wanted it local to this definition. Can I just lambda abstract out the
Exactly.
frequency parameter?
Yes, exactly. Okay, so you were all able to do this example?
So if you say in that program frequency equals H slider something,
Yes.
and then use frequency, there's only one slider, there's only one value of frequency, it's only one point at a time.
Okay, good point.
But if you use H slider twice, there will be two sliders,
No.
one frequency.
No,
No,
only one.
only one.
Yes.
It uses freak of the identity.
Even if you duplicate H slider or frac the same, it's only one slider, because you need to respect the fact that if you write A minus A, it should be 0.
Well, that's a statement of faith.
Yes. Yes.
Oh, is there a string concatenation operator so you can program
No.
and generate
No.
slider names?
No, but you can parameterize strings with numbers, but there is no, for example, I will show how to, I will need to go fast now, but I will show you how you can do that.
So all those numbers in the definitions are signals. So I could
Exactly.
have a slider, those parameters are next to the slider takes. I
Yeah,
can
but-
give it, are those like default minimum and maximum?
Yeah, they are all signals, but this one, the compiler will check that there are constant signals.
And if they're not constant, what does it
They
do?
will complain.
So they're not really signals if they have to be constant.
There are constant signals.
Okay.
Yeah, the compiler will have sometimes check for constant signal, control rate signals, the boundary of signals, etc. So you have a range. But the idea is that, okay, even if you have constant, not to create a different type, you have constant signals. But obviously, if you want to, you would like to change the boundaries of a slider, then you create a slider between 0 and 1, and you do the interpolation with a real signal then. Okay, so
efficient.
Yeah. Okay, I need to accelerate a little bit. Okay, so programming by composition. So you all recognize the Moog synthesizer, don't you? And you all recognize an ENIAC computer. So just to say that programming by patching is quite familiar. And so it's the base of languages like MaxMSP. But you see, it can be a mess, patch. And especially in MaxMSP, not the latest versions, but there was a period where the fact to change the diagram was changing the semantics. So for example, you had a large patch on the large screen, and you switched to a smaller screen, and things were rearranged. And then the semantics of the patch was changed by this simple fact. So it was the only language in the world with such a strange behavior.
It's called graphical programming.
Yes. Okay, so in Faust you can only do very structured block diagrams because you have an algebraic approach to block diagrams composition, function composition. So basically everything is based on these 5 operations: the split, the merge, the sequential composition, parallel composition, and recursive composition. So just to give you an idea, so here's the Faust expression. So you have 2 and 3 in parallel.
Is recursive composition like staging it somehow? What is recursive?
It's recursive in the sense that you feed back the output signal into the input of an expression. So it's create loops in the circuit.
I mean, these loops, are they limited so that to stop you from having like circular dependencies?
You cannot create with this operation. You take 2 things. And basically, you connect the output of one to the input of the other, and the output of the other to the input of the first one. But you introduce automatically a 1 sample delay, so it's always computable.
Okay.
That was your question, I guess.
Does that mean you could cause it? Could you act? Is it safe in the sense that you could?
Yes.
Could I have a memory leak by doing that?
No, it's impossible.
Okay.
And you can only create causal programs.
So they're causal, but they have a limited memory as well.
Yes. Well, yes. The compiler must be able to determine the boundary of any signal that is produced.
So if you create an increasing sequence of integers, the compiler will complain?
If you create no, it will complain if you try to use that as a delay line, as a delay of a delay line, because then it will say, okay, this has no boundary, so I cannot allocate memory, etc.
So does that one sample delay cause trouble sometimes? Because you could imagine that you can have static analysis and say that actually there is already a delay inside the boxes, and therefore I can have instantaneous feedback.
Yes, it's not that cause problems, but you need to decrease if you have another delay, you need to decrease it, so to speak, to take it into account. Probably, maybe some better solution could come out, but this one is quite. You don't have to stick to the problem. So basically, you can find cases where it's boring to attack.
I mean, if there were physical cables, there would be a small delay anyway, because there's a limit to the speed of electrons travelling down a wire.
Yes, but no other lines have delays on them here. That's the only delay that's introduced behind the scenes.
But anyway, the solution is when you have recursion, you need anyway at least 1 sample delay, otherwise it's not computable. So this is an example of using the tilde operation, the recursive the loop operation. So what we have here, we have the plus operation, we have the underscore. So the underscore is the identity function. It's a cable, so to speak, perfect cable. Okay. And here we have the tilde operation. The tilde operation takes the output of plus connected to the input of the cable via one sample delay represented by the small square here. And then connect the output of the cable to the first input of the plus. And this is an integrator. It integrates the incoming signal. Okay.
Actually, it looks modulo decoding of the integers.
Yes, sure.
It's bounded.
Yes. Yeah, but
So if I want, could I multiply, can I tell what the sample rate is from the program? So can I,
yes.
so I would, if I wanted to actually integrate, I would want to scale it scale the additions according to how long, or since the last sample.
Yes, you have access to the sampling rate, and for example, if you want to create an oscillator with a frequency expressed in hertz, for example, you need to know the sampling rate. And there you have in the library, you have access to external variables, so to speak, and there is one external variable which is initialized with the sampling rate. Okay, so if you have any of this diagram here, it's very easy to compute the semantics of this diagram. You start by saying, okay, let's give a name here and call that y of t. This one is delay, it's y of t minus 1. Then we know that the output here is y of t minus 1 plus 1. So we have y of t equal y of t minus 1 plus 1. Yes?
Right, at least one of the ones is not explicitly in the code, so could you change that delay, for example, to be delay by 2? Y of t minus
Oh, yes.
2? So where's
Yes.
2 though?
So here instead, let me do that on the online compiler. For example, let's call that. Yeah. Okay, so the process we have was process equal 1 plus tilde underscore semicolon. Okay. If we look at the diagram, we have the diagram block diagram. Okay, now here we have one sample delay, but we want to add another sample delay, so we have two sample delay, okay? So you can use the, so here instead of using a cable, you use the at operation that introduces a delay. So you can write at 1. So we tilde the plus with another operation which is not a cable but a one sample delay. So let's check that. Let me show you the, let's remove this.
Is at sign a shorthand for tilde with just do nothing?
Huh?
At sign is a shorthand for tilde where it forwards things?
No. The add sign here is just to add the feedback signal to 1. Okay, if you look at the diagram, you will see. You see here it is. So the plus is really used. It's used to use this signal and to add these two signals. It's not a placeholder. It's really an important operation.
So I mean, underscore is equivalent to @1.
Sorry?
Underscore is equivalent to @1.
No. Underscore is equivalent to identity function.
So so @0.
At 0, exactly. Okay, so if
two sample delays.
yes, so we can ask the automatic documentation if we want to check. You can. Let me explain the role of this automatic documentation. In the field in our field of computer music, you do a lot of pieces that now are really depending of the technology. So how do you preserve these pieces? Okay, you can keep all the files, etc.
It's broken now.
It takes time.
No, it's really broken.
Ah. No, it's okay for me. Or maybe you should restart your section. So we have a problem of preservation. And you can preserve the files, but it's not enough because the languages, etc., are always evolving, especially in the field of music creation, artistic creation. So programming languages used to do music composition or sound synthesis are not good languages to preserve. So you need something very stable. So the idea of this part here is to remove the language and keep the mathematics, so to speak, because the mathematics will be, anyway, simple mathematics, and they will be enough to preserve all the meaning of a Faust program. So this is what this automatic documentation does. So you see, generate a LaTeX file, and you see that here you have 2 samples delayed. And here you have a special plus notation to indicate that this is an integer addition, it's not the mathematical addition, and this is explained later into the document. So here you have a document that explains everything you need to know to re-implement in a different language the code that you have in Faust.
So I've experienced here that if you use this infinitely increasing integers as the frequency, then it is rounded? Or?
Yes.
But also it goes up and down, so it seems to be...
No, that's because it's the way the integer behaves. You know?
Yeah, the signal
Yes.
at negative frequency is the same signal as positive frequency.
Yeah, I needed clever people to... No, what I meant is that the semantic of that plus with respect to your command about preserving things, the semantic of the plus, because it's an integer, it depends on what architecture you are running the program. It's like
yes, but here it's explained in the way that all the architecture are all 32 bits integer operation in common computers are done the same way, and this is explained here. You see?
It says 2 to the 32.
Huh?
So it'll wrap after 2 to the 32.
Yes, he say here with n equal 32.
Is that what we heard just a minute ago?
I don't remember what we heard, but yeah, probably yes.
So it takes a second or two to do 2 to the 32 samples?
No, more than because you have yeah, less than a second.
Less than a second.
Yeah. Well,
There's
more than a second to do all the trick.
it's what is it? 48 kilohertz is standard audio sample, right?
Okay, so let me.
I think what you're hearing there is aliasing.
Okay, let me explain the various operations. So the parallel composition has no constraint on the number of inputs and outputs. Ah yes, I need to stop. Okay, so let's skip that. Maybe I'm just going to show you some different tools that you could use to make Faust programs. So in particular, I'm going to try to make a quick demo of another tool which is called Faustlive, which embeds the Faust compiler. So the problem that we have, because we are dealing with people that are not computer scientists, if you ask them to install Xcode and all the SDK, etc., it's very complex for most of them. So Faustlive is a solution that it's compiled, but it embeds the compiler. And it's also a cross-platform application. It exists on Windows, Mac, and Linux. So let me show you how Faustlive works very quickly. So you create an empty window, and you can drop a Faust program into a window, and it's compiled on the fly. Okay. Let's do a more complex stuff here. We start with a noise generator. From a noise generator, you can create a string sound. then from this you can create a harp sound, a harp instrument, so to speak.
From this, you mean they're combined?
Huh?
From this, you mean they're combined?
Yes, well, the basis was the sound, the noise generator, then you filter that.
Can you show the source of the one of the DSP file?
Yes, I can show you this.
This one.
So the noise generator is this one, just one line. The string is this one. It's a little bit more complex. Then we can create, so the harp is this one. Oh, so, but interestingly here we have a pentatonic scale and expressed as a function of degrees like we were discussing in the previous presentation. Okay, and then from that we are going to create this Kisan application. And last thing is that if you are on the same network than me, the cloud, then will be able to control this application. Just from a smartphone, if you are on the same network, you can flash the QR code and you can control this application.
Several people control it at once?
Yes, well, it will be a mess, but...
So so there's also a URL there.
That's, yes.
So is it just a sort of simple, you send it a packet and it does a thing? I mean, what's the protocol?
Okay, so
Like
who
suppose
is
they're in
doing that?
default.
Good. Let's put some sound. So with this application you create loops. So if you go here, you stop all the loops, and then you can progressively So because we are using a Faustlive and it's connected using Jack, you can combine applications together. So I'm going to put a reverb here. And I'm going to connect the two things. So instead of going, so I'm going to disconnect this one. And this one go to this one. Okay, so now it's going to a reverb. Okay, but while this is running, I can change the behavior because we have this, this embedded compiler. I will drop another effect and it will be replaced while running by the new one. So for example, here I have a wah-wah. And you switch to the wah-wah. Okay. And then when you are happy with that, for example, you can export for an Android phone. And you generate an instrument on the Android. Unfortunately, I have no time to show you that, but that's very fun.
Can you hook it up to MIDI?
Yes.
So I could get a MIDI keyboard.
Exactly, exactly. And we have ways to control the polyphony, so instead of doing a whole synthesizer, you can just discard one voice. And if you are in polyphonic mode, it creates a polyphonic synthesizer.
Another question about the MIDI. Since you said everything's a signal, can you read a signal? So supposing someone's placing code in closure or whatever, to run the code in closure, can you use that closure code as a controller, using just like audio in basically as your signal?
You don't have to use audio in to do that. You could, but you have a system of messages. For example, you can use OSC to control if you are doing OSC, you can use OSC to control. Like for example, here the application is controlled by the HTTP protocol. So basically it embeds a web server that serves the page, so that you can have the user interface and use HTTP. So you can use anything. Currently we have MIDI, we have HTTP, we have OSC, and that's it. But you could imagine to have others.
You could play this for your guitar and make it sound like
Yeah, yeah, exactly. Okay, so sorry for, yeah.
I was just going to say, how useful is the Jack Live program for actually live coding? Can you throw text literally at it from text editor? Does it handle errors gracefully?
I won't say that. Well, error is complicated, and I would say that the support for error message is not very good in Faust, especially if the error are not a syntactic error, but in the phase of the lambda calculus phase, so to speak. So what if you throw something with an error, it will keep the old. You will have a pop-up window saying that there is a syntax error, and you will keep the running program. Previous running program.
That's quite great. As long as it doesn't kill it.
No, it doesn't kill it. Yeah. Okay, so thank you.